Alright, so we're doing the second video for the review sheet, and we're going to be talking about limits and piecewise functions. So we're at section 4 on your review sheet, and we want to remember that a limit is a value that your function may approach if you approach a certain x value. So your limit is a y value, and if your function has a piecewise component to it, and at the place that you're trying to approach on the x-axis, from the right and the left you're approaching two different places on the y-axis, that's when we say a limit does not exist. So the function value doesn't have to exist for a limit to exist. You can have a function that looks like this, and when you approach this x equals 4 from the left or the right, you're approaching the same y value. You don't have to actually get there, so there doesn't have to be a dot there. You just have to be approaching it from both sides. So that's what we're going to be looking at, but not graphically. We're going to be doing it algebraically. So what we want to remember is the first step is always to try to plug a value in. The value you're approaching, try to plug it in. And unless you get 0 over 0, you will have your answer. Because 0 over 0 is what we're going to call the indeterminate form. It's the form that won't give us an answer. We'll have to do a little bit more work. But any other answer we will use as our limit. So if we get 0 over 5, we'll say the limit is 0. If we get 5 over 0, we'll say the limit doesn't exist. But 0 over 0 is a form that we have to work more with in order to be able to come up with an answer. A limit of 0 over 0 does not mean, when you plug in, 0 over 0 does not mean the limit doesn't exist. It just means we have a little more work to do. So if we look at A here, we're going to plug in 7, and we're going to see what the square root of 7 plus 2 minus 1 over 7 is. And we're going to realize that we get a number that looks like 2/7, and that's where we stop. That is our limit. But if we try the same thing on B, we're going to get 27 minus 27 over 3 minus 3, and that means keep going. There's more work to do to find out what this limit is. So the more work you need to do here is you want to factor. So hopefully you remember how to factor a cubed minus b cubed. If not, it factors like x minus 3 times x squared plus 3x plus 9. And once it's factored, we can see why it was going to 0 over 0 and divide those factors out, because as long as we don't let x be 3, these divide out to 1. And we're only approaching 3. We don't have to get there. So we'll divide them out, and now we'll plug 3 in again for our x's. And if you do that, you will end up with 9 plus 9 plus 9, and we will get a limit of 27. So even though it was 0 over 0, there really was a limit. The answer for C has to do with the piecewise function, what the piecewise function does around the number -2. So hopefully you remember that this absolute value is a piecewise. It looks like x plus 2 as long as you keep to numbers that are greater than or equal to -2. But if you decide to use numbers less than -2, then your value that comes out of your function will be the exact opposite of x plus 2. Because of that, when we look at our function that we're talking about, and we take a limit from the left of -2, we write that with a little minus here, we are on this piece of our numerator. So our numerator looks like this, while our denominator looks like x plus 2, because it doesn't change depending on your values of x. And that means that if we divide these two out, because we're not going to actually use -2, we're just going to get close to -2, we can see the limit is -1 from the left. So as long as the limit from the right is -1, we'll be good. So let's try it from the right. Now we're going to be on this top piece. But the denominator's not going to change. It is x plus 2 no matter what. And now we realize, whoops, the limit from the right is 1. So our function, as you come close to the number -2, is coming at a y value of -1 from the left, and it's coming at a y value of +1 from the right. And actually, if you graphed it, it's coming at a horizontal. But you don't even need to know that. They're just approaching two different values here. And we can't even use -2 because it would be undefined. So this is what it looks like for the limit to not exist. It does not exist. Moving on to a radical function. We've done these before as well. And what happens with these is if we plug in 0 and realize we're going to get 0 over 0, we need another kind of fix. And it isn't factoring, it is using the conjugate, which is sort of like unfactoring. So we're going to multiply the top by its conjugate, which means we need to multiply the bottom by its conjugate, or the top's conjugate, so that we're multiplying by the number 1. And when we multiply the top, we end up with x plus 9 times itself. If they're both under a square root, that means we're just going to get x plus 9. And then -3 times +3 is going to be -9. And on the denominators, we're going to have x times the conjugate. And we're not going to distribute the x in because we're going to realize that it can divide out. So if I distribute it in, I will be working backward. So now once it's all said and done and I have this thing simplified, I can take the limit as x approaches 3 or 0, which is what I was supposed to do. And now when I plug in 0, I won't get 0 over 0. I will get 1 over, this is going to be the square root of 9, which is 3, plus 3, I'll get 1 over 6. So my limiting value is 1 over 6. And last but not least, a piecewise function written as a piecewise function. We're going to do the same thing we did on C. We're going to take the limit from the left and the limit from the right of this number 8, which is where my function breaks apart, and see if we get the same number. So from the left, we are using numbers less than 8. We're going to be on this piece. And from the right, we're going to be on the other piece. But when we take the limit of this as x approaches 8, we're going to get 1/4 of 8 minus 1, which is 2 minus 1, which is 1. And here we're going to get the opposite of 8 plus 9, which is also 1. So since the limit from the left equals the limit from the right, we're going to say the limit is the number 1. So that was a quick review of limits. Next section has to do with derivatives. So good news is you're not going to have to do a derivative by definition, but you will have to use all the rules that we have for derivatives and decide which one makes the most sense. So if we look at number 5a, it seems like we might need the product rule. I have a function times a function. But unless one of these functions has some kind of power on it, like a square or a cube or a square root, the easiest way to do this is to do a rewrite. And we're going to FOIL it. 4x times x cubed, 4x times -2x squared, -3 times x cubed, -3 times 2x squared. And we can combine the x cubed terms into a -11. So once this is all rewritten, then we can take the derivative just using the simple power rule. And that will lead us to 16x cubed minus 33x squared plus 12x. and that is our derivative. But we can't do that on b. B is not as easy because we have two functions. One is called f and one is called the square root of x squared plus 1. And we cannot distribute into a square root. We can't take that x into the square root. So what we're going to have to do instead is the product rule. So we're going to call our first function x and our second function x squared plus 1. And I'm just going to rename this so that we don't get confused about what f is. So this is how we said we would handle it. We'll take each's derivative, and we're not going to forget, because we've just done integrals, we're not going to forget that chain rule when we take the derivative of g. So now we have our four pieces that we can put together for the derivative for b. We're going to take f times g prime. And I see 1/2 and 2 are going to multiply to 1, so I'm just going to get rid of them. F times g prime I can write as x squared, and x squared plus 1 to the negative 1/2, that product. And g times f prime is going to be x squared plus 1 to the positive 1/2. And if that's all I need to do for my problem, that's the derivative. If I might need to get critical values, then I'm going to factor out the lowest degree on my x squared plus 1 factor and get x squared plus, now this will become x squared plus 1 to the first, because 1/2 minus negative 1/2 is 1. So then I could keep on going if I needed to find critical values. So C looks like a quotient. Probably need the quotient rule, and I do. However, looking at the problem, I could factor it and maybe things will simplify before I jump into the quotient rule. So I'm going to factor it into x minus 3 and x plus 1, and x minus 1 and x plus 1, so that I can divide out the common factor. And now, as long as I don't let x be negative 1, I can do the quotient rule on x minus 3 over x minus 1. So the quotient rule says take the denominator and square it. Start with the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And so when I distribute and combine up here, I'm going to end up with the number 2 and my denominator x minus 1 squared. D. D is a function living inside a 7th power. So this is when we use the general power rule. So the general power rule for D is going to say move the 7 down in front and drop it to 6. So now I'm not at the 7th power, I'm at the 6th power. Don't change the function that's inside, but do multiply on its derivative. So the derivative of x squared is 2x, and the derivative of 1 over x is negative 1 over x squared. If you're wondering how I did that, I just thought about x. 1 over x is x to the negative 1. Move the negative down and change the degree to negative 2. So that's the general power rule, and it's done. E and F are both implicit differentiation, and I know that because the y that's stuck here in the midst of this term and the y squared, that's another term. So when I've got two y's and I can't solve for y, I'm going to have to do it implicitly. So I'm going to go left to right. Everything I encounter, I will take its derivative with respect to x. So x squared will become 2x. I'll look at this as a product of two functions requiring the product rule. So if my first function is 3x, the derivative of the second is dy dx. Plus, if my second function is y, the derivative of the first is 3. Now I'll move on to y squared, and I'm going to use the general power rule just like we did here in D. the 2 will come down, the degree will change to 1, and the chain rule will multiply on a dy dx. And then I move to the other side and take the derivative of 10, which is 0. So now I need to solve this mess for dy dx. That would be my derivative. So the first thing I'm going to do is factor the dy dx out of the left. And I put a 1 here that looks like a prime, so I'm going to erase that just so it's not confusing. Factoring dy dx out of these two terms. And the other terms, since I don't have dy dx, I'm going to have to move them to the other side and make them negative. And now I'll divide by 3x plus 2y. And there's my derivative. So f is a lot like that. F has implicit differentiation in it. The reason I put it on there, even though we've done one like it, is the minus in front of the product rule. So I want to make sure that you are careful when you see this negative in front of a product. You're going to distribute your negative. So I'm going to take the derivative. I'm going to go left to right. 3x squared is going to give me 9x, or 3x cubed is going to give me 9x squared. And I'm going to do the product rule in parentheses, so I distribute my negative. The first function times the derivative of the second, plus the second times the derivative of the first. And then here's the general power rule again. It's the 1/2 power. So I'm going to bring the 1/2 down, drop the degree to negative 1/2, and multiply on the derivative of y, which is dy dx. So now when I do my next step, I have to be careful to realize that x dy dx is negative, and so is y. So when I go to factor out, I'm going to factor out dy dx and be left with negative x plus 1/2 y to the negative 1/2. And then I'm going to have, on the other side, a negative 9x squared, but a positive y. And then when I divide for my final answer, I will end up with that. So implicit differentiation, but being careful about the product rule giving me a sum that I needed to distribute the negative into. All right, so looking at G, we have got a quotient, function divided by function. And I cannot divide this x with that x because this is living in a square and this is living in a log, and I can't get into those functions to divide out. So what I'm going to do is the quotient rule. So I'm going to square the denominator, the ln of x squared, and those parentheses aren't necessary, so I'm just dropping them for what I'm writing down now. Then I start with my denominator, the ln of x, times the derivative of my numerator, 2x, minus my numerator times the derivative of ln of x. So what you need to remember is the derivative of ln of x is 1 over x. So now I'm going to take a minute to simplify it, only because if this were an extrema question and I needed critical values, I want to make sure you know how to do that. So I have a 2x times an ln of x minus this, which multiplies to x. And that means that I have an x here and an x here that I could factor out if I wanted to. So if I were looking for critical values, this would be the way I'd want to think about my function. 2 ln of x minus 1 would be able to give me a critical value, and so would x. But don't forget, the domain is greater than 0, so the fact that there's an x here and a critical value of 0 is not going to help you. The critical value that will help you comes from here. Moving on to H, we have a product. So I'm going to make my first function 4x and my second function e to the negative x. And my derivative, I'm going to keep the 4x and multiply on the derivative of e to the negative x, which requires the chain rule. E to the negative x times negative 1 plus e to the negative x times the derivative of 4x, which is 4. And again, if I were looking for critical values, you'd want to factor out a 4 and an e to the negative x. And that would help you get toward those critical values. I is another quotient, and so we would do that with the quotient rule. We would square the denominator, which would turn it into x to the 4th. We'd start with the denominator. Derivative of the numerator is e to the x, minus the numerator is e to the x times the derivative of the denominator. And you could simplify that as well by factoring. J is a little tricky. The easiest way to tackle J is to rewrite it, the entire denominator to the negative 1. Once it's rewritten like that, then you can use the general power rule. The thing is, you're going to have to remember when you go to take the derivative of the inside that then you need the product rule. So the bigger picture is the negative 1 will come down and change to a negative 2. The function inside will not change, but when you multiply on its derivative, you're going to have to keep the first function as it is, times the derivative of the second, which requires the chain rule, plus the second times the derivative of the first. And that is your derivative for J. And then last but not least, K, you want to do a rewrite on. So because you have the log of a product, you could rewrite it as the log of x squared plus the log of x plus 1 to the 1/2. And then you could go even further, writing it as 2 times the log of x plus 1/2 times the log of x plus 1. And the reason that that helps is now the derivative is fairly simple. 2 times the derivative of ln of x, which is 1 over x, plus 1/2 times the derivative of the ln of x plus 1, which is 1 over x plus 1, times 1, the derivative of x plus 1. So the rewrite made the derivative a lot easier. So I'm going to stop the video with that, and I'll pick up with number 6 for video number 3.